Hi folks, I'm on a little bit early here. A few things I'm going to cover today. I want to talk about OSS, fine-tuning it with reasoning. I'll touch on Kyutai, a speech-to-text model that I'm hoping to make a video on, but most of all, I want to talk about ARC. There were 2 new submissions in the public leaderboard this week that significantly improved on the scores from last time. And I'm going to go through each of those. There are relatively short blogs on each topic. They're actually somewhat similar to the approach Lewis and I are taking of writing Python programs. Now we're focused on the private leaderboard where you're limited to using specific computers, 4 L4s for 12 hours, whereas in the public leaderboard you can use up to $10,000 worth of compute. If you're joining, drop me a comment or question on those topics or on something else. I'm streaming on YouTube, also on LinkedIn and X as well. Welcome to anyone on those platforms. Hello. And I'll get started with the content in just a few minutes on the hour. So say hello if you're in the chat. Let me know any questions. This here's a tweet from Elon Musk when the ARC prize solutions came out this week, the better approaches. His comment here on how he thinks XAI has a chance of reaching AGI with Grok 5. Of course, the best solutions here are using Grok models in the public leaderboard. So all of these, this is the score in ARC AGI 2, and you can see all 3 top scores. This one here is just Grok on its own, no fancy engineering. These ones are fancy engineering, and all of them are using Grok. You can see GPT-5 is down here. My screenshot stop sharing. Reshare that. We'll get started in a minute or two. Say hello if you're just joining. I can see a few in there. I'm going to be talking about, I want to update a bit on what the best model is to fine-tune. Talk about OSS, briefly touch on speech-to-text model. I'm currently preparing a video on how to fine-tune Kyutai, and then I'll talk about ARC. I'm going to go through 2 approaches that came out this week, all very similar. And yeah, let me know any questions if you're in the chat. It can be about this or something else. Am I working on ARC? Yes. Oh, hi, Matthew. I believe you've chatted with Lewis a few times. I like your paper a lot on the latent space work. If so, which version? Yeah, working on version 2. I haven't looked at version 3 at all, really. Just trying to focus. There's only a few weeks, 5-6 weeks left before November 3rd. So focused on ARC AGI 2. Focused on writing Python programs with Lewis. I'll say a few things about that. Maybe comment on some learnings from the blogs that are up here. Okay, music too loud, you're right. Music way too loud. Let me fix that and then I'm going to get started. Okay. I think that's better now. Let me know if it's not. Tiago, thanks for the comment. So folks, going to get started. I am mostly going to talk about ARC on this. I'm going to talk about the 2 approaches that were submitted to the public leaderboard. I'll describe what public versus private is, and I'll go through those approaches. One is by Eric Bang, and the other is by Jeremy Berman. They are somewhat similar. They both write programs, and then they execute the programs. Jeremy writes natural language programs, and Eric writes Python programs. So I'll talk about those in quite a bit of detail. I first just wanted to say one or two things about GPT OSS and about Kyutai. The reason I keep talking about OSS is because people want to know what is the best model to be fine-tuning. And that, of course, changes as models get better and new ones get released. And one of the ones that is best for, well, it's best in a lot of cases right now for fine-tuning is GPT OSS 20B. The reason is it's quite small. It fits on a single GPU in most cases. It's very fast for inference because it's a mixture of experts. It only activates a few billion parameters. So you get fast inference, but it's, you know, a reasonably sized 20 billion parameter model. And it's very strong. If you go to artificial analysis and you look at the models that are here, you can see GPT OSS 120B is among the top models on intelligence. And actually the 20B model, which I just showed, is not too far down here. But there's a bottleneck right now on tuning this model, which I want to mention. I don't think it's quite solved yet. The bottleneck is that typically you tune in 16 bits, but this model was designed by OpenAI to be natively in 4 bits. So it's an MXFP8 model, or sorry, MXFP4. It's a special type of floating point 4-bit model. And because of that, it would be nice to be able to tune in that same precision and not have to expand it up to 16 bits. So currently when you tune it, you can tune it in that lower precision, the original precision with Unsloth. But as of yet, and it's almost been released, you cannot cleanly merge back down to 4 bits to have a final model that's in 4 bits. So I'll just show you here. You can find this notebook on the Unsloth repo on GitHub. But if you go down to the very end of the notebook, which is where you merge LoRa weights, if you're not familiar with LoRa, maybe look at the last live stream, or take a look at the fine tuning playlist on the channel. But you can see here where you merge, and this is where you merge and push to hub. And the save method is called MXFP4, which means you're saving it to the precision of the original model, which is what you want. If you're not able to save to the original precision, then you're going to have a 16-bit model. And I'll show you what that looks like. So if you have an original 4-bit model, it's going to look like this. You've got 3 shards to reach about 4 to 5 gigabytes. So you've about 15 gigabytes of weights. That's going to fit on a lot of GPUs. But if you save in 16 bits, here's a 16-bit version of this same model. You can see we have about 9 shards, 4 to 5 each. Sorry, my screen just moved. But basically that means you're up around 8 times 5. You're up around 40 gigabytes instead of just 20. So if you're going to be training, you ideally want to be able to merge down to that size that the model originally was, and you're going to want to be able to do inference. So all I'm saying is, if you're trying to do this, I don't think it's quite working yet. I tried it this morning, but hopefully soon this will be working on PyPy as well. If you're tuning with Unsloth, then Unsloth will be recommended over transformers. I have a video on tuning this model using transformers. You can check it out on this channel, but I'll probably do an updated video on Unsloth just so you can benefit from this here. There's something else I want to say as well, which is that reasoning models are generally, the open source ones are not as robust as the private ones. If you give complex prompts, like trying to solve ARC to a lot of reasoning models, including OSS 20B, you often will not get a meaningfully structured response. You might end up hitting max tokens, or you might end up just with a blank program, is what I've seen. So some of these reasoning models are just not all that robust. Another model I'll point to here is the Qwen 4B thinking model. It's an updated version of the Qwen 4B model, which is both reasoning and non-reasoning. In principle, the thinking model here should be stronger. I've read a bit online. It does produce a lot more tokens. I think it tends to produce around 10,000 reasoning tokens, whereas this one produces just a few. Well, not just a few, probably around 1,000 or 2,000. It really depends on the answer, but I have tried out this thinking model, and in many cases it produces so many tokens, I just hit my max tokens that I've set, if I've set 32,000. So using these reasoning models is not that straightforward. Even now, I need to get more experience on tuning them to be able to recommend, okay, you should just tune reasoning models and expect to get good results. So that's all I want to say on OSS. Let me know if you have any questions, and I'll keep you updated on the next live stream if that functionality of merging back down to the 4-bit format is working. Very briefly, before I move to ARC, I just want to mention something about speech to text. Speech-to-text models, of course, the most well-known one is Whisper. There is now Voxtral, a version from Mistral, and there is Kyutai, I believe, a French company. Not sure if I'm pronouncing that right, but they have a series of streaming speech-to-text models. You can check out a video. You'll find that in the audio playlist on Trellis Research channel here. And I talk about how these models work. But what I don't do is cover how to fine-tune them. And fine-tuning them is a little tricky because it's not natively supported by Unsloth or transformers even. You can load the model now with transformers. That's what I've got here, a transformers version of the model. But running inference is straightforward. If you want to train, though, you have to figure out how to timestamp your data and set it up so that it's collated and can be fed into the model. And this is not entirely trivial, but I just wanted to mention I am planning a video on this, so it will be possible to tune a streaming speech-to-text model. Now, if you didn't see my earlier video, the key difference with streaming is it's going to transcribe what I'm saying as I speak, whereas with Whisper transcribes a full block of 30 seconds. So Whisper is not well built for streaming. If you want to stream with Whisper, you literally have to take a chunk of text, and then when I say some more, you have to again process the next 30 seconds, kind of overlapping. So you end up redoing a lot of compute. It's not an autoregressive model like the Kyutai model is. So this is quite an interesting characteristic that it can stream. And it would be nice if people were able to fine tune it. So that's what I'm hoping to do. Okay, so ARC Prize. Let's talk a bit about this. Put any questions in. I am working on ARC Prize myself with Lewis Hemans. You can see a video on YouTube on this channel as well. I'm referencing a lot of my videos today about our initial thoughts. We are writing Python programs. So we get large language models to write solutions to tasks that look like this here. This is a page I often go to. And a little tip, if any of you are working with ARC Prize challenges, say you have a challenge here, you can find the code for any challenge and just paste it into your URL, and then it'll display the challenge here. So these tasks involve patterns from input to output. You see a number of what are called training examples, and then you have to complete a test example here, following the same transformation as is on the left-hand side. And yeah, the way Lewis and I are looking at this is getting an LLM to take an input of these programs, usually described as numbers 0 to 9 in grids, and then writing a Python transformation from the input to the output. And it's typical not just to get the LLM to write one program, but to sample the LLM in parallel to get many programs, say 100 programs, and run all of them on the original inputs and see if they match on the original outputs, the training examples. And if that's the case, you've got a good indication that maybe the program will be correct when you roll it forward on the test here. So that's in principle the program approach. There are a lot of tricks and tips around that, some of which we're going to see now in the two approaches I'll cover today. So if you look at ArcAGI and the leaderboard so far on ArcAGI 2, which is this year's competition, there is ArcAGI 3, which is more like solving computer games, Atari type games. I haven't looked at that too much, but that presumably is even harder. I'm going to pull up the leaderboard here, and I'll just show you how models have been doing on the public and the private leaderboard. So we can compare those, because there are two competitions. So here, if I actually go to ARC Prize and I check the leaderboard, you can just focus on looking at ArcAGI 2 here. So you can, of course, check ArcAGI 1. And there are two leaderboards. One leaderboard, you can spend up to $10,000 on solving all the tasks. And the other leaderboard, you are limited to a Kaggle environment for 12 hours with 4 L4s. L4s are Ada Lovelace generation, so before Hopper. They're reasonably okay GPUs. Probably the 4 L4s together are equivalent to some fraction of a H200, maybe a quarter the throughput of a H200. Unfortunately, the interlink between the L4s is not particularly fast, so you're not easily able to run a model that's spread across the GPUs, because you'll lose too much. You'll have too much latency in transferring weights if you do something like tensor parallel between the 4 GPUs. So you're probably incentivized to run 4 copies of a full model in parallel rather than run one big model across all 4 and have that latency hit. So that means you're basically limited to a model that at best is probably something like OSS 20B. That's possibly the most powerful model you could run. And that's going to be weaker, as I showed, than the leading model, which is Grok 5 High, which is being used on the public leaderboard, because that's, well, it is the strongest model, not just here on artificial intelligence, but also for solving ARC. I will come back. I see a question here related to LoRa, which I'll come back to in a second. So this leaderboard here has been, well, originally it was dominated by O3 and O4, the reasoning series of models from OpenAI. Claude came out with a reasonable score. Claude 4 Sonnet and Opus came out close to 10% on ARC AGI 2. Sorry, the font is so small here. GPT 5 High recently out at 10%, but Grok 4, when it came out, was a leading score, and that's 15%. And what this score specifically means is that on 120 held out tasks, which are not shared with the public, this model is scoring, when it's allowed 2 attempts per task, it's scoring 16%. And when I say 2 attempts per task, you can submit any 2, and if either one is correct, you'll be marked correct on that task. Something else I should say is that the tasks can have multiple multiple test outputs. So you can have a partial score on a task. If there are 3 test outputs, you could score 1/3. So the score here of 16% could be 16% of 120 tasks, but it could be also a combination of some partial tasks that are correct. It's kind of a technicality. But the big news this week is that on the public leaderboard, so not in the private competition where I'm focused, not that I'm in anywhere close to a leading position on the private competition, I'm way down in the single digits, Lewis and I working on our program's approach. But on the public competition, Eric and Jeremy have scored up 25 to almost 30%. So they've almost doubled what Grok 4 is doing if you don't apply any harness. So this here is a very simple approach. You take the prompt just being a description of the grids, lay them out, and you ask Grok to reason and directly output the correct test output. Whereas in these approaches, which we'll see, a lot more is being done to get the model to refine, take multiple steps, do sampling in parallel to try and boost the score. So one comment is, I suppose it's interesting that there's a 2x improvement. Is that a huge improvement? Maybe, yeah, I'm not sure. I kind of want to say it's still within the same realm of what the base model is able to do on its own. So a lot of the performance here, and I think Elon is kind of right when he says this. Well, he has a few comments about these scores here, but I think probably Grok does deserve a lot of the credit for the scores that are coming here. And then, yes, of course, the refinement strategy is bringing some bonus on top of that. So with that, I think I'll just get into each of these 2 approaches. I'll start off with Eric's approach, which is writing Python programs. And then I'll talk a bit about Jeremy's approach, where he's writing the programs in natural language and having the LLM apply that natural language program to convert inputs into outputs. Maybe just briefly some nomenclature on these tasks, because I find it's hard to talk about them otherwise. A task, this is a task. There are 120 of them. It's the whole thing on this screen here. An example is a pair. So this is an example pair. You have training example pairs and you have test example pairs. Sometimes you've just one test example, but sometimes you have to solve multiple, like 3 in this case here. And we call these grids. So you have grids. There are 2 grids, input and output in each example. There can be up to 10 training examples. And I'm not sure how many test examples there can be. There can definitely be 1, 2, or 3. Maybe there can be more as well. Maybe it's limited to 3, I'm not entirely sure. But yeah, 10 train examples and a few test examples, let's say. So let me get started then in with this blog, which is Eric's blog. So Eric's approach compared to Jeremy's, they both score very well. They score similarly, but Eric's is actually more compute efficient, I think by a factor of more than maybe roughly around 5 or better. And it's hard to know exactly. You can see there's a lot of sampling in Jeremy's approach, and maybe it would score similarly with a bit less sampling. It's hard to ablate all of the parameters. So yeah, I wouldn't say with really high confidence I know exactly why one is more efficient than the other. So the easiest way to take a look after the intro of what Eric is doing is just to look at the graph. And I'll open it up in a new tab, and we can kind of walk through what's happening. Let me just quickly answer this question here on LoRa. I know I'm veering off. With fine-tuning LoRa, can this be used to add repo knowledge directly into the model instead of RAG? Yes, this is correct. That would be one reason to do some fine-tuning, is because you want to impart knowledge on the model. Now, often just including context might be better and more robust. So fine-tuning might end up being a case of you want to add domain knowledge, or you want to add certain structure, or you want to add certain ways about reasoning. So that's why you might look at fine-tuning. So here with Eric's approach, we have an LLM. This is the LLM here. It takes in a prompt. The prompt is going to instruct the model to generate a program, and that program is hopefully going to solve the set of challenges here. And indeed, we can test the program on the training inputs and see if it's correct on the training inputs, and that gives us an indication of whether it might be correct on the test input. And if it's got all of the training inputs correct, we'll probably select it then and roll it forward on the test to get the test output here. So it might be useful if we just, I don't know if he has an example of a prompt here. No, I don't. I see one in Jeremy. So we look at the prompt when Jeremy has it. But essentially what Eric is doing is he's passing in the task, which is a description of these inputs and output grids, and also a description of the tests that need to be solved. So all the test input grids here. And he's also passing in a seed program. So he's starting off with a seed. We'll talk about where the seed comes from, but think of it as provide a program to capture the transformation from these inputs to outputs. And then you would have input 1, output 1. Then you would have the test grid inputs, and then you would have sample program. So he's starting off already giving a sample program. We'll talk about where that comes from, but yeah, he's giving a sample program and saying then, please refine, improve the program. So that's a quick sketch of what he's doing. And he does this many times. So we'll generate a few programs, not in the same prompt, not in the same call to the LLM, but in parallelized calls. And that's going to give multiple programs. And then he calculates the accuracy score. Now, the accuracy score just means taking the program, applying it to each of these input grids individually, and getting the output grids. And then comparing the output grids from the program to the actual training output grids. So that's the score. If it gets all of these, then it's going to score 100%. If it gets 2, it's going to score 66%. If it scores 100%, he's in a great place, because now he can perhaps say, okay, I have got 100% on the train examples. And by the way, I think this maybe should say 100% on train examples, because you can't, of course, see the test outputs. Unless this is during pre-training, then it could make sense. But if it's during the submission itself, you're going to have to check on the train outputs. And if it gets all the train outputs correct, then you're going to say, right, I'm going to stop and I'm going to apply it over here. So that's loosely that step. Now, he then takes the correct program and feeds it back here. So in very simple terms, this is how Eric's approach is working. You sample some programs, you check which ones are correct. If you get a correct one, you're happy, you move on to the next task. If you don't get a correct one, you can go back around for another turn. But the key thing here is, how do you choose what program to seed? What's the initial program that you want to pick? when you generate the prompt, what's the sample program you put in here? And the answer is, he picks the sample program from 2 sources, and he picks it by ranking in 2 different ways. So we'll take a look at the 2 sources and then the ranking as well. Okay, so the first source of programs is when he goes through this loop, he's generating new programs, and they provide a source in later stages for a pool that can serve to seed. So initially, this is obviously not useful because you haven't generated anything. So it's only going to be useful as you're going through the submission. As you go through tasks, you're going to accumulate programs, and then you're going to use those, put them in the pool essentially. Well, you put some of them in the pool, and you'll consider those to seed your generation here. So that's the first source, is during the competition using essentially programs from other tasks. Now, the second source is that before the competition starts, he will run this loop on a set of training tasks. The tasks actually that the competition provides, ARC AGI 2 training. And this is kind of surprising, because it basically says I'm solving a given task, like this task here, but as a first step, I'm actually going to roll forward programs from other tasks in the training set. So for example, if I go to the training set, I will generate in advance of the competition some programs that solve these problems. And I'm going to take programs for unrelated tasks, and I'm going to use them for the task that I'm trying to solve at the moment. And yeah, that's his idea. So basically, he's got 2 different ways to provide seed programs. One is in pre-training, he'll run the training problems, generate lots of programs for different tasks, unrelated tasks, and hope that some of those are somewhat similar, so the program is useful. And then the second source is during the competition, use programs from that same task that obviously weren't fully correct, because then you'd move on, and also use programs from other tasks. So this is the 2 sources of the pool. And the question then is, if he has this pool, how does he decide which program to use as the seed? Because he could have many, hundreds or thousands. And the answer is 2 ways. One is he will first rank based on correctness. So if a program, let's say I'm trying to solve this task here. Well, let's go to the hard one again. I'm trying to solve this task here, and I have a program, it's solving 66%. If that's the highest scoring program I have, I'm going to take that one. Now, if I have 2 programs that score that, or as is probably going to be the case in the competition because the tasks are hard, you'll have 0 programs that solve, you'll have no programs that solve any of these. What he will then use is pixel match. So he will take the output generated by the program, compare it to the actual training output, and he will do the pixel match percentage and pick as a seed. So for this program here, he will pick the best program from all of the pre-training programs he's generated and all of the programs he's generated more or less during the competition, and use that as the seed here to improve upon. Now, obviously picking a good program is useful, because to the extent your starting point is good, that's probably going to make the refinement easier. So having a good heuristic, his heuristics are correctness percentage and then pixel match. Having a good heuristic is pretty important to get good performance. Now, I did a little bit of ablation. So I took some programs from the ARC AGI 1, that's last year's training set, and ran them all on some of the problems from the eval set. And what I saw was that you do get some positive signal from the pixel match. So those programs that you do see that there are some programs, even from unrelated tasks, that have higher pixel match than others. Often the program that has the highest pixel match is a pass-through program. It's one where the program literally says, take the input and copy it as the output, because a lot of tasks have similarity between the input and output, especially if they're the same grid size, which they don't have to be. So it's not entirely obvious that pixel match would help a lot. I think there is some signal, because there is a fairly big difference in pixel match when you run all training programs on a given eval task. So I think it probably does make sense as a helpful heuristic. And previously I wasn't really convinced by pixel match, but I never really thought of just running all the previous programs, and now I'm more convinced that it does make sense. The other thing I'd say is it's not trivial. I asked Eric this on Substack. and thanks to Eric for the responses there as well. It was pretty fast to get back. Executing the programs is not trivial. If you have, say, 1,000, there's 1,000 tasks in training for ArcAGI 2. If you had a program for each of those, which would be hard to get, by the way, but if you had a program for half of them, you would have to run 500 programs, test 500 of them on each eval task. And yeah, that's a lot of CPU work, and it's not trivial. You've programs that end up taking quite a bit longer than, well, some of the programs are just unsuited to the task and they take so long, you'll have to kill the program after a timeout, and that ends up burning up a lot of your CPU time. So not necessarily trivial to just execute a bunch of programs. And it's basically doing a brute force search. Basically, you're doing a brute force search here to get a good seed before you do some program generation. So that's kind of a first look at the whole approach. I'll briefly talk about some of the ablations he did. So here, can I increase my screen width a little bit? Let's see, beautiful. So he compares here, and this is, by the way, on ArcAGI 1 training tasks, which are a lot easier. They're easier than ArcAGI 1 eval, and they're way easier than ArcAGI 2 eval. And he compares GPT-4o, and then GPT-5, and then Grok 4. And you can see here that he's getting 7.5 or 20% or 27 with GPT-4o, and then he's getting about 3 times the score here with GPT-5 or Grok 4. Now, I don't say with this with high confidence because I haven't done enough work, but I think the gap you see on ArcAGI 2 between these latest reasoning and the older models is even larger. So often you just score 0 with GPT-4o, and so you get very little signal. And also, just because you see an improvement in GPT-4o so let's look at one specific ablation. So here, between the first row and the second row, he's including, when he's asking for an improvement here, he's providing not just the sample program, but he's also saying, by the way, the sample program gave these wrong outputs. And here is the diff. The diff is the difference between the correct and the wrong. So he will show on a pixel basis which pixels were wrong with that test program. So in that ablation there, he's changing just 2 things. No, he's changing just one thing. He's adding a program diff, and he's going from 7.5 to 20%. So that tells you GPT-4o really benefits from seeing a diff in this example on ArcAGI 1. Does that apply to ArcAGI 2 when you use stronger models? You would have to test it, because possibly the reasoning is good enough with these stronger models that they can just kind of create the diff by themselves, which of course is possible because you're giving them the program. And very often, I should have said this, very often when you give the sample program, you also give the sample program outputs. Now, in the private competition, this is a bit annoying because the more context you add here, the worse the models tend to perform, because it's hard to get reasoning models to be stable with longer context. Well, I won't say that categorically. It's not necessarily worse because you're adding context that can be useful, but it adds context. Also, more context means slower generation, so you're using up more compute. So that kind of goes against you as well. Let's see, are there anything else I want to say on ablations here? I mentioned he ranks the seed programs, so he ranks the choice of seed program to slot in here based on correctness on the training examples, but he also ranks them then based on the pixel match. And what you're seeing here in this ablation, when you go from the second row to the third row, is he's actually doing a kind of a combined score. So he's combining the pixel match with the correctness. And yeah, he's seeing some difference there. It's not the largest of the differences he's seeing overall. Now, what else do I want to say? Yeah, he has some nice comments on, so rather than use a heuristic here, the heuristic being correctness and then pixel match, you could think, well, maybe it's better to use a neural net, and the neural net can suggest which of all these pool of programs I should use. And in a sense, if you fine tune a model on that pool of programs, then your model is the neural net that's recommending which seed you should start with. So that's a way to think about it. And Lewis and I are doing we are trying to train a model like that. So we hadn't thought about it that way, but one way you can think about it is you're really just suggesting a program. And then you've got a trade-off. Do you want to spend lots of CPU time running all these programs to calculate their correctness and their pixel match? Or do you want to just do a few forward passes on a neural net? So you've got this CPU versus GPU compute trade-off around picking the best seed that's going to be used to kick off your program here. So yeah, there's a further idea which pulls in a somewhat independent approach called certain searching latent space. Don't know if Matthew you're still on. Saw you were there earlier. But this paper by Clément and Matthew is a very nice neural approach for finding a program, and the program is actually described in latent space, and potentially this could be applied, as Eric is saying, to try and get a quick suggestion of which program you might want to choose. So with that, I think I'm going to move on to cover the approach by Jeremy, which scores higher but is less compute efficient. Now, one reason you might suspect why this approach is more efficient than Jeremy's is because you start off with a seed program. And if that seed brings you close to where you want to be, then that's going to save you compute because you need less iterations. The other thing is that Eric's approach is not a crazy Monte Carlo where he does crazy sampling. He's got relatively few numbers of samples. He's got 5 samples here, which is quite a small number. Now they are on reasoning models, so they're going to be slow samples, but 5 is quite small. And he doesn't even loop around that many times. So he'll go all the way around 120 tasks, and then he'll go back around a second time, I think. And in the pre-training, he's not going crazy either. He's just doing, I think, 1 program and 1 go around. So yeah, pretty efficient overall. I mean, it's immediately obvious why it's compute efficient, because there just are very few calls, but exactly why he's able to get away with that is more difficult to pinpoint. It could be because the seed programs are good. To say that, you would need to really understand more about how good a heuristic the pixel match is, because when you do the first round on ArcAGI 2, those problems are really hard. You're almost certainly not going to have a program in your library that solves it. You're almost certainly not going to have a program that comes close, that even gets a partial correct. So you're just relying on pixel match basically as a heuristic to kind of get you started. So yeah, further areas of research, if you can come up with better heuristics for ranking programs other than pixel match, that would be useful in principle. Not easy. In ARC, you basically have a big gap between, you've got a program that writes absolute garbage, and then you've got a program that gets one of the examples correct. And once you've got one correct, you're kind of not too far off getting more of them correct, and you've a chance of hill climbing. By the way, I wouldn't even say that with entire confidence. That's more my mental model and a little bit anecdotal based on what I've seen. All right, so we'll move on here to Jeremy's approach. And as I said, it's similar in the sense that it uses Grok. It's similar in that it writes programs, and maybe that's where the similarity stops. It's more sampling heavy. Yeah, let's just jump into what it is. So I think it's good I've explained how the Python approach works, because if you understand that, you'll understand how the language model works. And the way the language model works is quite simple. So now if we go, this was Eric's approach, but with Eric's approach, we say write a Python program. So this is the Eric approach here. If we go to the Jeremy approach, we will say write a natural language program to capture the transformation. And actually, the first time around, Jeremy will not seed. So this is already a fairly big difference. Let's maximize this. Jeremy initially will just ask for an initial program, I believe. So we start up here and we just do an initial generation. So there's no sample program. There's no sample program outputs. There's no request for refinement. There's just the input grids here, the test input grid. Of course, the train output grids are also included, all those pairs. And then we're just asking for a natural language program. Now, whereas a Python program would look like def transform, and then some kind of flips, something like that. A natural language program would look like, check if there are 3 yellow dots, and if so, put some magenta dots 2 below them. That's an example of a natural language program. So he will get the LLM to generate a natural language program, and then he will execute the program. So what does execution look like? Because it's not running Python code. Execution, and this is me a little bit extrapolating or guessing exactly how he does it. I would have to look more carefully at his code. But even if this isn't what he does, maybe it's an interesting way to do it. The execution would involve also an LLM. And you say, okay, here are some instructions for transforming an input grid to an output grid. And then let's give the instructions. Now apply that to this grid. And the grid might simply be something like yellow, black, black, and then maybe something like black, 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 something like that here. And now the LLM is going to respond. Sorry, my screen's just gone off on me again. And the LLM is going to respond hopefully with the correct answer, which in this case, because I gave the instruction, would be changing this one here to magenta. So basically you can use the LLM to execute as an executor. Is it accurate? I guess it's pretty accurate because Jeremy's approach works. It's a strong LLM. It's of course stochastic, so you can't expect that it's always going to get it. But I guess if the instructions are good, it's going to be able to apply the instruction to the input grid and give you the output grid. And the nice thing about if you do this is you can apply it separately to each input without showing the LLM during execution the output. And that can allow you then to score versus the output. And if you can do that, you can verify essentially whether you've got the correct program description. So you can verify whether this program is correct. And if the execution is correct on each of the training ones, you can then apply it to the test and submit that answer. So it's very analogous to the Python approach, but you've kind of decomposed the LLM steps so that it's verifiable. So this is pretty nice. That concept by itself, I think, is very nice. And actually, when I heard that concept, I was thinking, God, yeah, I should spend more time writing natural language programs, because maybe that's the hiccup. Maybe Lewis and I are having trouble because Python is just not kind of expressive enough, or it's hard to write some of these challenges correctly in Python. But then when I saw Eric's approach, I was thinking, well, actually, Eric is getting basically the same score and he's still using Python. So this kind of indicates to me that natural language, definitely a cool idea, but maybe not essential. By the way, let me know any questions there. I think you can submit somehow on LinkedIn and X as well, possibly, definitely on YouTube. Okay, so that's the first step. But then Jeremy does a lot of sampling. So this is kind of reminiscent of multi-armed bandit or MCTS type approaches. He will take, see if he's got a perfect solution. If he does, he just moves to the end. By perfect, it means the execution of the program, the natural language program, solves all these. But if not, he goes to refinement. And here he does quite a bit of sampling. He will, and I'll show you the prompt, he will take the program, he will provide ASCII diff of what it predicts for the outputs versus the actual truth, and then he'll ask for refinement. So this again is pretty smart. And let's take a look at how the revision works. So here, he's giving the inputs, he's giving the outputs, he's giving the example pairs, he's giving the test. And he's giving here, this is the assistant providing the instruction. Sorry, it's probably quite small. And now he's saying, okay, your previous instructions were applied, but they didn't give the right grids. And here he's showing what the differences were. And he's giving this ASCII diff. Ooh, yeah. He's giving this ASCII diff here, which is saying, okay, the 0 is right. The 1 should have been a 0. The 0 should have been a 3. The 2 should have been a 1. And yeah. So he likes diffs too. Eric likes diffs. Jeremy likes diffs. Maybe diffs are a good idea. Probably should do more of it myself. And he manages to, well, he uses that to refine. Let's go back out again to the chart. So he'll use that and he'll sample the 5 top instructions. And I presume he is ranking them by partials, correct? I'm actually not sure how he is ranking after partials, if he's using pixel match or something else. Maybe he says it. But top 5, let's see what he says. Take the top 5 instructions, highest scoring. So I'm not entirely sure how he picks the top 5. A fitness score. To evaluate these, this can be a fitness score based on how many training examples it solves correctly or partially, counting the percentage of cells. Yeah, I'm not sure if he's just picking at random from the ones if he doesn't have any partially correct. So that's not clear. Maybe he does use a second layer like pixel match or something else. That's an important question. I'll probably post a comment on the blog. So once he's done that, and he doesn't just sample that once, he samples that multiple times. Let's go back to the graph here. So if he's not got a perfect solution, he does individual revision, he evaluates and scores. If he does have a good solution, of course, he finishes. And if he doesn't, he does pooled revision. Pooled revision is the same thing, except now, instead of just looking at one of the grids, he's looking at multiple grids. So, instead of taking one program, he's sampling multiple programs and putting them into the same prompt. So I'll just show you what that prompt looks like here. So it's down below, and let's see, instructions 1, instructions 2, and let's see where he's got the programs written. Okay, yeah, you can see there's instructions 1, which is reflect the grid across the vertical axis, and then the other ones leave the grid unchanged. So the idea here is, well, you have a few different program ideas. Can the LLM synthesize those to give a correct program? Makes very good intuitive sense. You could probably go one step further and you could say, well, if you have a program that's right on the first training grid and a program that's right on the second one, maybe you can put them both in and ask the LLM to fuse them and find some program that will hopefully solve both or all of them ideally. So yeah, this is kind of a summary of his approach. And then he gets to the end and yeah, he's got up to 40 attempts, 30 initial, 5 individual plus 5 pooled. So that's his sampling strategy, 30 candidates, 5, and then 5 more. So he's kind of got a fairly broad breadth first search. Then he's got 5, and then he's got 5. Now, something I want to say here is actually his prompting is quite straightforward. This is not a very big prompt. He's just putting in an input of the grids with numbers. He's not putting in an ASCII version. He's not putting in a base 64. If you look at Eric's here, you can check. Actually, each input grid is represented in multiple formats, namely grid dimensions, base 64, ASCII, and Python nested list. So Eric is just giving it everything. He's putting everything into that prompt to trying to give it as much information as possible. So you have 2 ways of thinking about this. One is give it as much info as possible. It will help. The other is, well, the more info you give, the more you're going to kind of overload it. And this is maybe more of an issue with weaker models than with stronger models. So my general comment here on ablations and kind of tricks, when you see new approaches come out, you will often see new tricks, but unfortunately it's quite hard to know exactly which tricks are the ones that really make the difference. Just for example, here, you might think, oh yeah, that's really making a difference, putting in base 64 image encoding. We're giving this multimodal model some image context, and that's really part of the reason why it's doing well. But then of course, you've got a great approach here from Jeremy that doesn't have any base 64 encoding and is doing great. Then you have Eric who's using a seed example at the start. Maybe that's boosting it, but then Jeremy doesn't even use that. So maybe the seed example is not so critical. Although the seed example clearly has to be critical. It depends on what point you consider it seed. You could say in Jeremy's approach, his 30 candidates are ultimately what's providing the seed. And maybe those seeds are a lot better than just considering all the programs from random other tasks. So yeah, that's pretty much it. There are a lot less ablations in Jeremy's blog. He talks a bit about, he gives some nice philosophical kind of thoughts on LLMs and how they've got domain specific knowledge. And if the reasoning is good in one domain, like, I don't know, cookery, and then in maths, unfortunately in the LLM weights, that reasoning is kind of disparate. Whereas in humans, we've managed to decompose and recompose and condense into one place, probably, our reasoning. So we are able to connect that to many different fields. Whereas in LLMs, they end up having reasoning over here and reasoning over here. So it ends up being not so generalizable. So kind of a nice comment there from Jeremy. So yeah, Roscoe, how's life? That is pretty much it on this ARC overview. What time is it? Yeah, it's 2:45. If there are any questions, let me know. I'll stay on for another second or two. I see a question from Roscoe. Yes, I talked about this. You can go back and look at the live stream at the start. I didn't show you how to do it because I can't do it myself yet. I'm getting some help from Kyutai on laying out the data loader. But yeah, I'm planning to fine tune the Kyutai TTS. Any other questions on ARC? Just let me know in the chat here. You can find these on Substack, Jeremy Berman. Interesting, they're both Substack. And then CT Pang. Yeah. Thanks, Kopiko. Yeah, Qti fine-tune is in the repo. There's a script I'm working on. So people who've got access to the repo from trials.com, you can see I'm working on it. I also am adding notes on OSS around fine-tuning that. Nice. Yeah. So the fine-tuning playlist is a good place to start. Go to the Trellis research channel. There are a number of playlists. There's one for fine-tuning. There's LLMs. There's one for video, audio, robotics, inference, evals. But that's a good place to go. Customer serving LLMs for FAQs. Set guardrails. Yeah. Setting guardrails for LLMs. Yeah, I mean, your basic, you can definitely stop certain words from being produced. I think you can do that with VLLM, but you have to think about, do you want to put a layer between the customer and between your API? And do you want that layer to actually be an LLM, maybe a fast LLM or some form of classifier? And that's obviously going to add latency. I do talk about that. You can find, I think it's called Llama Guard. There's a video on that. I know Llama Guard's a bit updated, but the concepts in that video are not really so much. So you can check that, Kopiko. All right, folks. Thanks everyone for joining. I'll chat to you all soon. Cheers.